Video lesson 10.2. So for this one, we're talking about exponential growth and decay. So first off, let's look at the do now. Let's actually graph these two functions that we see here. So let's make a table for the first one. So I'll do that one here in blue. So f of x is equal to x squared. So let's plug that into the calculator. Let's get an x and y table, right, for this function. So here, let's see if we plug this in. 0, 1, 2, 3, 4, that should be good. We've got 0, 1, 4, 9, 16. Alright, so again, plugging that into the calculator, took my y values, and we're going to plot those. So we got 0, 0, 1, 1, 2, 4, 3, 9, and 416. So this is the function that we get. Hopefully draw a relatively nice curve here. All right, there we go. And then again, arrow at the top because it continues on from there. All right, let's do another one here for g of x. It's 2 to the x. So we're going to do x and g of x, aka the y. So we'll do the same value, 0, 1, 2, 3, 4. And I've got 1, 2, 4, 8, 16. So let's plot those. 0, 0, 1, 2, 2, 4, 3, 8, 4, 16, like so. So you can see here, unfortunately it does not make the nicest straight lines here for some strange reason, but you get the general picture. So you see how they're similar to each other, right? But they are not the same. All right, so this one here, this function here, where x is the base, where it's an exponent. So each of the times you plug in a value, you're squaring that value. So the next one, for example, like 5 would be 25. Right, and 6 would be 36. If I do it over here, right, the growth rate is growing more rapidly. So if I was to plug 5 in here, that's 2 raised to the 5th. That's 2 times itself 5 times. So that's going to be 32. Right, and if I did that 2 to the 6th, that's going to be even larger. That would be what, 64. Right, that's times another 2. So each time in this example, this is doubling, right, as you go. Where here it's not. See, it goes, it goes up 1, then it goes up 3, then up 5. The rate of change here is changing within each of them. Where here, each of them is doubling for this part. So that's your exponential growth here for those. So if you took them to find something like this, where it says here, what's the value when x is 20, we could just plug them in, because based on here, it looks like this will be off our graph anyway. So we could plug them in and see what values we get. So for, I'll do it here. So for f of x, if I plug 20 in, I get 20 squared, which is 400. If I say g of 20, that's 2 to the 20th power. So that means that's 2 20 times, right? That's going to be a very largely growing number. I got in 1,048,576. Right? So you can see how with more time the exponential function grows significantly more rapidly as we go. From there, the exponent, the x squared, it's still growing, and it's still growing, it is getting larger and larger as you go, but the exponential function here, where the exponent is the x, it's just going to grow at a much more rapid rate as x gets larger. Right. So when dealing with exponential functions, whether it be word problems or not, we need to understand the formula and how that kind of relates to it. So when dealing with these, it's important to be able to differentiate between a growth and a decay. And that is the b value, right? That's the b factor. So we talked before about it's a growth when the b value, right, is greater than 1, right? It's greater than 1. Well, more specifically, when you are adding the rate here. So this b value, right, 1 plus r, when that rate is represented in this scenario of word problems, you're going to see it as a 1 plus r value. So for here, we're going to get a function that looks like this. So we'll say f of x is equal to a. Again, normally we just put b, but now we got a specific rate that we're referring to. So we're going to refer to that as 1 plus r to the x power. All right. Again, this will allow us to have a growth. For decay, right, we'll do it over here. We'll say f of x is equal to a, again, instead of b, we're going to replace that with 1 minus r to the x. And again, remember this was when b was between 0 and 1. So it's a fraction less than 1, but bigger than 0. Right, so these are your formulas, again, respectively, growth and decay. And we want to make sure we understand each of the things. So we talked in the previous videos that a was your initial value. All right. So in this case, for this context, right, that's the amount before the growth or decay, where it's starting, right? The r in this one here is your growth rate or your decay rate. Typically that is given to you as a percent, so you got to convert the percent to a decimal. All right, just so you know. And lastly, we have our x, which is in this case the number of times the number of time intervals that have passed. All right, so those are the key things. Again, b was our growth rate, right, or decay rate, but specifically the r value is the actual rate, right, for that part. So let's look at this first two examples where they just really want us to understand the terminology and be able to decipher. So if we look at this first one, which scenario represents an exponential growth? So here I'm looking for something that is growing exponentially. So it's growing, in this case, starts off slowly and then will get larger and larger and larger and larger. So from here, so a water tank is filled at a rate of 2 gallons per minute. That would be a constant rate of change. So that's linear, right? So that would not work. This would be linear, right? Vine grows 6 inches each week. Again, that's linear, right? So that's not going to work. The species of flies doubles in population every month during the summer. So it's doubling. So and then each month it's doubling again. So that's going to be your exponential growth, right? From there. But let's just look at 4. A car increases distance from a garage as travels at consistent speed of 25 miles per hour. That's just basically a flat line, right? Its distance is changing, but its speed is not. So again, we have no exponential growth with respect to that. So number 2, they're giving us information specifically about a checking account. And they gave us the equation, and they want to know what does each of the pieces mean. So in this one, they specifically are looking for the y-intercept, right? And what does it represent? So again, the y-intercept, aka your initial value, right? We want to look for that. for here. So that's your initial, and the initial value was the A term, right? So that's this part here. And we're looking for, so that gives us an answer choice of either 3 or 4. So I can get rid of these. Those are your rates. And what was it? So 7,000 would represent, in this case, the initial amount that the account started at, which is option 4. I'm sorry, 3 for this example. For that. So again, these types of questions, if you know the definitions or the characteristics of an exponential function, then these are the types of questions that'll be, quick and easy for you to be able to decipher. All right. Let's look at number 3. So here, notice that in the function, we don't have a plus or a minus. We don't have a 1 plus r or 1 minus r, at least not at first glance, right? We do actually have that there, but it's just not given to us as a plus or a minus scenario. They've taken it here. That's your b value is 1.05. So we need to take that, and we can figure out what that situation means. So it's bigger than 1, right? So the b value is bigger than 1 here, right? So that means there's a growth. So we now know that there's a growth going on. All right, so that would be where b equaled 1 plus r, right? So if I put the 1.05 here in for b, if I minused 1 over, right, then I know that I now have 0.05 is r, right? So if I scoop 2 decimal places to the right, that's going to tell me that the r equals 5%. So that means that we now have a 5% growth occurring in this scenario. All right. So again, they do give it to us. It's just not in that specific form. They've combined it. So you got to pay attention to it. Now, if this was less than 1, right, then it would be a decay. We would have said b equals 1 minus r, set it equal to that, solved for r, and then you'd have the percent that it is decaying. So again, 2 different things happening there in that type of thought process. This one specifically is a growth, which is a good representation of like how to find those things. All right, next one. Here they have a sample of a chemical compound, which is given in the function p of t is equal to 500 times 0.4 t, where pt represents the number of milligrams of a substance and t represents the time in years. So in the function p of t, explain what 0.4 and 500 represent. Well, one of these is really quickly we could answer real fast, and that's the 500 part, right? Because that's my a term, and we know that a is our initial amount. So 500, right, equals initial, in this case, amount of the compound. So that's first part. To figure out what the 0.4 represents, right, that's our b term. So in this case, it's less than 1, so b is less than 1. So that means it's a decay. So I can say b is equal to 1 minus r. So 0.4 is equal to 1 minus r. All right, so if I minus the 1 from both sides, I get negative 0.6 is equal to negative r. If I divide both sides by negative 1, right, I'm going to get r to equal 0.6, which would mean that that's a 60% decay. So that's the 60% decay. That's what's happening here. But specifically, it wants to know what the 0.4 is. Well, if 60% is decaying, right, that would mean that the other amount, what's left over, is what remains. So out of the 100%, if 60% was utilized, that would mean then here that 40% remains. Right? So that's, again, when they've calculated it, that's actually what the 0.4 value represents. Again, we're plugging in the rate, but it actually ends up being that it's a 40% left over from there, or the remaining compound in this case for there. So again, a little trickier the way they worded it and the way they kind of came about, but again, easy to find the pieces once you know the terminology and the specific characteristics of the exponential function. All right, let's try another one here. So we've got this one here. So we've got the value of this record collection is increasing at a rate of 3% per year. The initial value of these collection is 4,000. Let's write an equation to find V, the value of the records after T years. So we're going to say V of T equals, we have an initial amount, right? We want, so we got A times, it's an increase, right? So it's going to be 1 plus our rate, right? So it's 1 plus R, right? To, in this case, to the X is going to represent, in this case, T, time. So let's plug in what we know. We've got an A value of 4,000. We know that R is 3%, which is 0.03. And T is time. T is what we don't have that. We just know what's occurring. Now the percent is in terms of years, but that's not our T value, right? That's just representing what the rate is, how it's being compounded. So in this scenario, this general formula is going to be V of T is equal to 4,000, 1 plus 0.03 raised to the T. And again, we can simplify that by just saying 4,000, 1 plus 0.03 is just 1.03 to the T. And there we go. We now have a general equation for this increasing or growth rate of this collection. Follow up to this is use the equation to determine how much money to the nearest dollar the record collection is worth after 4 years. So once I have this, all I got to do now is take the years and plug it in here for T. So T is going to equal 4. So if we take our function here, V of 4, it'd be 4,000, 1.03, and that's going to be to the 4th. So take this, we can plug this into the calculator. Again, I recommend doing it in parts. You know, some students like to just plug everything in right away, but I like to actually do this part first, take that answer, then multiply by 4,000. Whichever one of that you want to do is perfectly fine with me, you know, as long as you do it correctly and carefully. But I've got here a value of 4,502, and it's money, and so we got 4 cents. Don't forget your dollar sign, and that would be what we have for the value of this record collection after 4 years. All right, let's do another one similar to that, because these are, you know, good questions to be able to, you know, come up with the equations and then utilize them. So we've got Mike bought a new car, $15,000. He drove it off a lot. His best friend Will told him that the car value just dropped by 15%, and that would continue to depreciate 15% at its current value each year. And let's make an equation for that. So unfortunately, there's truth to that. The second you buy your car and you drive it off a lot, it does depreciate in value. But let's see what this situation will represent. So let's see. I'm going to say, it doesn't, you know, they don't specifically say, so I'll say C of T. So C for car value and T for time. So C of T is going to equal, right? Well, in this case, we have a decrease, right? It's depreciating. All right, so we've got a times 1 minus r to the t. So c of t will equal, well, a was 15,000 and r is 15%, which will be 0.15. So I've got 15,000 times 1 minus 0.15 to the t. If I actually subtract the 1 minus 0.15, I should get 0.85. So c of t is going to equal 15,000.85 raised to the t. So there's my general equation of this depreciating car value that we have in this condition. So then the question now says, can we use this formula to determine Mike's car after 5 years? So now I'm going to take that and I'm going to say C of 5. So that's going to be 15,000 times 0.85 to the 5th power. Let's plug that into the calculator and see what we get. I'm getting, again, it's money, so $, 60, say 6,655 and 58 cents. So after 5 years, his car has depreciated, not half, but pretty close to being half of that. So, that's unfortunately, pretty rapid decrease in its value for that one. But again, there's truth to that. Like I said, once you drive your car off the lot, it did in fact depreciate in value. So take the opportunity to rewatch any of the videos if you need any to go over anything in more depth, and don't forget to utilize the practice problems for better understanding.